Well, hello, and welcome back to another episode of Quantitative Bytes. So today I'd really like to continue the series that we started on developing things using turtle graphics in C++. So in the previous episode and the one before that, if you've seen those, if not, I'll put a link here and you can go and have a look. We looked at developing a class in C++ that would allow us to implement turtle graphics, and we talked about what turtle graphics was and why it's interesting, and showed some simple examples of what we can go on to do with that. Now, I always said that really the purpose of doing that, and the reason I went through the process of developing the class to do turtle graphics, was so that we could go on to explore a series of fractal curves that we can make using that technique. And good news, that's what we're going to do today. So today we're going to look specifically at von Koch curves. I believe it's pronounced Koch. Von Koch was a Swedish mathematician, so I'm sure if there are some Swedish people out there, maybe you correct me on my pronunciation, but I think it's von Koch. Anyway, he is famous for the von Koch snowflake, which is a particularly famous fractal. What I'm going to do today, I want to spend a bit of time just introducing exactly what the von Koch curve is, or the von Koch snowflake, and exactly what it is. And then I want to talk a bit about how it's actually formed and how we generate it. And in this episode today, I'm going to talk about creating a class, which we're going to call a generator class, that is going to be responsible for creating the fundamental component from which the whole fractal curve is actually generated. And then in the next episode, we're actually going to finish that off and then create the code to create the actual final snowflake. So I don't want to talk for too long, except one last thing I just want to say. If you haven't subscribed to my channel already, then please do so you don't have to miss any future videos. And if you like this video, please smash that like button. Yeah, it really makes a difference, and actually makes a big difference to me. It's always good to know that people like the content I'm making. Anyway, so that's enough of an introduction. Let's skip over to the computer and have a look at what von Koch curves really are all about. Let's go. This is the famous von Koch snowflake, or von Koch, or Koch as it's sometimes pronounced, I believe, but I believe von Koch is the correct pronunciation, so we're going to go with that. So this is the famous von Koch snowflake. From an algorithm point of view, it's really quite an interesting shape to look at generating. This requires a recursive algorithm in order to create it, and I just think it's actually rather interesting and, to be honest, a little bit fun. So what I want to go through first is just a basic introduction to what the von Koch snowflake really is and how it's formed, and we're going to talk a bit about the actual geometry and how we're going to go about creating the generator class that we just spoke about. So the von Koch curve, or snowflake, the von Koch snowflake, is actually made out of two principal components, and these are the initiator. So this is just a simple equilateral triangle in the most basic case, which we call the initiator, and then we apply the generator. We're going to talk about that in a moment, to each side of the initiator. So what happens is that we get the first generation. So we've applied this shape here. So we see this shape here consisting of 1, 2, 3, 4 edges, and we've applied that to each side of our equilateral triangle, which gives this classic star pattern. And then for generation 2, simply all we do is we take each of these edges and we apply that same shape to each of those edges in turn, which gives us this. So this would be generation 2, and then we would do the same thing again, we just apply exactly that same shape, like so, to each one of these edges, and that gives generation 3, which is the picture that we just saw at the beginning. So that is the basic principle of the von Koch curve. The initiator, I suppose, there could be considered to be generation 0, but just the terminology that I've chosen to use, that's the initiator, and then generation 1 and 2, as we've just seen. So what's this generator that I've been talking about? So here we go. So we have, to create that example, we have the initiator, which is our equilateral triangle, and then we have the generator that looks like this. So to create the curve that we've just seen, this generator shape, or line, was applied to each side of the initiator, and that gave us generation 1. And then we applied the same whole generator to each edge of the resulting generator, and so on and so forth, to get generations 2, 3, and so on. Obviously, we can go to as many levels of detail as we wish. What I want to focus on today is just the generator. Then in the next episode we're going to come back to look at the initiator and exactly how to implement the recursive algorithm to actually create the curve. But today we're going to focus on the generator, and I want to start by just really explaining about the geometry of this. And this is one of those things. There are numerous ways that this could be implemented in code. And what I've set out to do is to create a class for the generator that is as generic as possible. So it's possible for the user of this class to specify a variety of different shapes and so on within certain limitations for the generator, which can then be applied to create a variety of different curves. Now, it was my choice to do it that way. I kind of like the challenge of writing code to be as generic as possible, and so that's really just what I set out to do. So the way I'm going to present of actually doing this might seem to be a bit more complicated than it necessarily needs to be, but as I say, it was really born out of an attempt to try to make something as generic as possible. So if we just focus on the generator, initially this is what we have, and we can see that the generator consists of 4 edges. So these are edge 1, edge 2, edge 3, and edge 4. In this particular case. Okay, as I've said, we're trying to keep things general, but let's explore this particular case and then we'll see how we can generalize that further later on. We also have 3 angles because we've created an equilateral triangle here. Okay, so we have obviously this angle here is 60, this angle is 60, this angle here is also obviously 60, but we don't need to specify that. If we specify these 2, then obviously this one has to be 60 as well because all the angles in a triangle add up to 180. So that's pretty basic. And we can also see that this is divided into 3 segments. Now I really want you to just pay a little bit of attention to the terminology I'm using here, because when we come to look at the code later on, that will really help. So these here are called edges. So from the start to here is edge 1, from there to there is edge 2. So each of the lines is an edge, but the whole shape is divided into a number of segments. Okay, we call these segment 1, segment 2, and segment 3 as shown. Okay, now all of the segments are of equal length. That's really important. And all of the edges are of equal length. And it is actually the edge length that we need to calculate because we're going to create this using turtle graphics. So what we're going to do is start from the starting point. We're going to point the turtle in a particular direction. We're going to set the edge length, and then we're going to call the step method that will move us across that length. So we need to know what that edge length is. They're all the same, so we only need to calculate the particular edge, the length of one edge, and then we know all of the others. So the challenge is, how do we actually calculate the edge length? Well, we need to consider everything that we actually know. So we know the location of the start point, and we know the location of the end point, and we know the location of 2, what I'm terming, calling nodes. Okay, so these nodes are the particular features so that the user can specify an angle at each node, and that describes the shape of the generator that we're trying to create. Okay, so in this case, the angle at node 1 is 60 degrees. The angle at node 2 actually isn't 60 degrees, it would be minus 120, because we want the angle that would make our turtle go from pointing in this direction to pointing in this direction. Notice that we don't need to define a 3rd node here because this segment is just assumed. So the first segment and the last segment, or the first edge and the last edge, are assumed to always connect to the starting point and the ending point respectively. So we only actually need to generate this particular shape. We only need to define 2 nodes, one here to say rotate 60 degrees and one here to say rotate minus 120 degrees. And when we step the turtle over each of those, we'll end up to here, and then the final edge will be created automatically. Okay? So the problem is that given the starting point and the end point, and we have n nodes, each of angle theta n, so we can have any number of nodes, and each node can have any angle associated with it. Given that, we need to calculate the edge length. How do we go about doing that? Issue that we have is that we need to calculate what the edge length will be for each of these edges. And we can do that very simply. If we know how many segments we have, remember that we divided this into 3 segments, as being segment 1, segment 2, and segment 3, then we know that the edge length has to simply be the total length, that's the distance from the start point to the end point, divided by the number of segments. So we need to calculate the number of segments. Now total length is easy, endpoint minus start point, we get that distance there, that's the total length. Now we know the number of segments is going to be at least 2 because we have this segment here from the start point and we have this segment here that goes to the end point. What we don't know though is exactly how many segments we need to create this central region, which is the area that the user can define. So the user can specify any number of nodes, and they can specify any angle at the nodes, and we therefore need to be able to calculate how many segments that is actually going to occupy. So in this particular case, we can do that quite simply, and it's really just a question of trigonometry. So we know that if we assume that the segment length is 1 here, so okay, and we simply then use trigonometry, we know that this distance from here to here is going to be 1 multiplied by the cosine of 60, and this distance from here to here is going to be 1 times the cosine of minus 120, because this is the minus 120 here, this is the angle through which we have to rotate the turtle to go from heading in this direction to heading in this direction, okay? So that's the angle we store at that node is minus 120. Now when we come to look at this in the code, we will see that what we do is we actually keep track of a cumulative angle. So we end up, the first node is 60, the second node is at minus 120, so that will be 60 plus minus 120, so minus 60. And of course the cosine of minus 120 or minus 60 is minus a half. So that gives minus a half, which is that distance there. So we can see we can calculate the number of segments quite easily. It's simply 2 plus the absolute value of the cosine of theta 1 plus the absolute value of the cosine of theta 2 in this scenario. So like I say, when we come to actually look at the code, we'll have a look at how we really how we do this, and we keep track of a cumulative angle rather than doing it this way. But in this particular case, this serves as a good illustration of the methodology that we're using. So that's 2 plus the absolute value of the cosine of 60 plus the absolute value of the cosine of minus 120, which gives 2 plus a half, which is 2 plus 1, which gives 3, which is of course the right answer, 1, 2 and 3 segments. So that's the method that we are broadly going to use, with the one exception that we are going to, as I say, calculate the cosine of the angle cumulatively as we go through each node, but we will cover that when we come to it in the code. So that's a basic outline really of what we're going to do and the geometry of what we're actually trying to solve. I think if anything about that is unclear, I think hopefully it will be clarified when we actually see how we do that in code. So let's do that now. Let's jump into the code and have a look at exactly what we need to do. Okay, so I have here, this is the code that we wrote in the previous episode. So this is capp.h and capp.cpp. So if you followed the previous episode, there's a link in the description below to the previous episode, then you should have the same code here. Now, we need to make some very minor changes to this. So one thing that we need to add to this is we're going to create a new class. Our generator class. So we will need to declare that. Now we're going to call it qbvk generator, like that, and we're going to call the instance of it vk for von Koch generator, like that. But we haven't actually defined that class yet, so let's save that. And now we're going to create a new file. So this is going to be qbvk generator.h. So we go with our include guards first, hash fndef qbvk generator h. If that's not defined already, then we define it qbvk generator h hash ndef. Okay, so I've gone ahead and saved that as qbvk generator.h. So let's have a look at what we actually need. First thing we need to do is we need to include vector. We're going to need that, and we're going to need to include our turtle class that we created in the previous episode, qbturtle.h. Oops, that's wrong, isn't it? That way, qbturtle.h, like so. And we're going to create our class, which is qbvk generator. And we are going to create some public functions. We need, first of all, the constructor destructor pair. We're probably not really going to use those very much, but it's good practice to have them, I think, anyway. And tilde for the destructor QBVK generator, just like that. And then we need functions to let the user specify the start point and the end point, and to add nodes, as we saw in the diagram. So we have void set start point, and that's going to accept a float x pars and float y pars, just like that. And void set end point, it's going to be float x pars and float y pars, just the same. Okay. And then we need a function, spell void correctly, that does help. Void add node float angle. Okay, so each node consists of just an angle. Now we're going to create a compute method that we're going to allow the user to call when they want to actually calculate all of the edge length that we've just talked about. We also need to store, we also have a function, that returns the number of edges. And finally, we need a function to allow us to get an edge. So get edge, and this is going to return x1, y1, x2, y2 for the start point and end points of the edge. So we simply define these as pointers to floats. So float x1, float star y1, and float star x2, and float star y2, and int index. Index is the index of the particular edge that we want to get. And we need to declare some private stuff. So first of all, we need storage for all of our data. So we're going to use std vector of type float, and we need to store a node angle. We store an angle at each node. Okay, and we have std vector of type float. We're going to store mx1, std vector float y1, and we're just going to do this for x2 and y2 as well. Oops, mx2 std vector float my2, just like so. We need an instance of our turtle class, so we create qbturtle mturtle, like so. And then we're also going to need to store start x and start y. Yep, and end x and end y is for the start and end points, and int num edges. Okay, that is everything that we need for our header file for QBVK generator. Okay, so we'll save that. And now let's make a new file. We're going to start fleshing out qbvkgenerator.cpp. So in order to save some time, I'm going to copy and paste some bits over here. So let's go ahead and save that. So the constructor and destructor, pretty basic. The only thing really that's worth noting there is that we specify the initial number of edges in the constructor as being 1. Okay, and then start point and end point, we have our functions to set those. Those are pretty basic. So set start point, and they do the same thing. Each accepts a float for x pos and y pos and simply stores those in the appropriate member variables accordingly. Add node is, okay, so we also have add node, which is a little bit different. So this accepts an angle, and it simply stores the angle into our array. So mnode angle dot pushback angle, so we simply store that. Yes, so if we look back at our diagram, we can see that we know we have this segment here and we have this segment here, regardless of however many there are in the middle. So we know that the number of edges is always going to start at 2. Okay. Before we get to the compute method, which is the one that really does all the work, there's some other just basic stuff that we're going to copy and paste in. Feel free to pause the video at any point to have a look at these. So num edges simply returns the number of edges, and get edge, which allows us to return an edge. So it accepts an index. It accepts 4 pointers corresponding to the values of where we're going to return x1, y1, x2, and y2, and it accepts an index being the number of the edge that we want to get. The first thing we do is check if that index is valid. If it isn't, then we simply return false. That's why this function is declared a type boolean. And otherwise we simply assign the values according to the index here and return true to indicate the process was successful. So that's that. So the interesting method, though, and that I'm most keen to talk about, is QBVK generator, : compute. So the compute method is where we're actually going to do the computation to calculate the number of segments and hence the edge length. First thing that we need to do is to reset any previously computed vertices. So these are the points that define all of our edges. Okay, so mx1 dot clear, my1 dot clear, mx2 dot clear, and my2 dot clear. Okay. Now we can compute x1, y1, and x2, y2 for each edge. Okay, so first of all, mx1, I'm going to push back m start x. Okay, so we know that the first vertex is always going to be the starting point. Okay, so my1 push back m start y, like so. Now, if the number of edges, if m num edges is equal to 1, okay, then we know that the next vertex is simply going to be our end point. So we simply do mx2 push back m end x, like so, and my2 push back m end y, like that. Okay. If, on the other hand, we have more edges than that, then we need to do a bit more. Okay, so now what we're going to do, we are going to compute the edge length. Okay. So let's put in a nice comment to say what we're going to do. We're going to compute the edge length, assuming that the distance from start to end is equal to 1. Initially, we're going to make that assumption, okay? So, just as we commented when we were looking at the presentation just now, we have to do first, we compute the number of segments that we must divide the whole length into, okay? And note that num_segs, that's the number of segments, starts at 2 because 2 corresponds to the edges that take us from the start point to the first node and from the last node to the end point. Okay? Okay, so notice we're defining num_segs initially as a float, okay, as a type float, and that is going to be really important. So we do float num_segs equals 2. Let's just move this up so you can see it more clearly. It's more in the center. So float num_segs equals 2. We also have a float cumulative angle starts out at 0. So notice that num_seg starts at 2. That's, as we've just commented there, cumulative angle starts at 0, okay. And now we're simply going to loop through each of our nodes, and remember we stored an angle at each node, so we can do that easily using this auto reference I in m node angle. So that will iterate through each entry in m node angle, and we simply do cumulative angle plus equals I, okay, and then num_segs is plus equals the absolute value using Fab's floating point absolute of the cosine of cumulative angle multiplied by, and this is just to convert to radians, is m pi divided by 180.0f and 3 brackets, okay, and save that. Right, now just check that, yes, I did include math.h. Okay, so what actually is happening there, this is what I mentioned about how we were going to use the cumulative angle rather than the actual angle. So if we look back at our diagram here, so what we have, we're assuming we know about this edge already, so we're now calculating the contribution of this edge. So what we're doing essentially is projecting it onto this axis between the start point and the end point, okay, by using the cosine of this angle. So we know that the cosine of 60 in this case gives a half, which is very clearly to there. Now, the cosine of minus 120 conveniently gives minus a half, which in this case would be right. But if this angle is something other than 60, and this angle is therefore obviously something other than minus 120, suppose this angle was 45, then this angle would have to be minus 90, then that's going to give very different results, because the cosine of minus 90 gives 0, which would clearly not be correct. But what we do instead is we keep a track of the cumulative angle. So we start with cumulative angle is equal to 0, and then when we consider the first node, we add 60 to it. Okay, so cumulative angle is now 60, and we take the cosine of that, which gives a half. And then we come to here, and the angle for our next node is minus 120. So our cumulative angle becomes 60 plus minus 120, which is minus 60. So we do the cosine of minus 60, which of course gives minus a half, which in this case is the same answer, but would be a technique that will work regardless of what angles that we actually specify. Again, if you draw that out with a pen and paper yourself, I think you'll see what we're doing. Essentially, we're calculating the angle of this from here, and then we're assuming that we have another segment here that begins from here and goes down like that. So we're calculating the contribution that each makes to this axis, which in this case just happens to be horizontal. I know that might seem a little bit confusing. As I say, I think if you sit down, work through it with a pen and paper, you'll see what's going on. Anyway, that's how we do that. Right. So now we're going to calculate our initial length. So we're going to compute init length, which is the length from the start point to the end point. Okay, that's an easy float. Init length is equal to the square root of m end x minus m start x multiplied by m end x minus m start x plus m end y minus m start y multiplied by m end y minus m start y. Okay, so that's just basic Pythagoras. Okay, and now we compute, oops, there we go. Now edge length, we're going to calculate edge length, is the length of each edge, obviously. Okay, and we compute that as float. Edge length is now equal to simply the initial length divided by number of segs that we've just calculated. So that gives us the length of each edge. Now, what we actually need to do now is to use our turtle to calculate the points x1, y1, x2, and y2 for each individual edge. Okay, so first of all, we're going to compute the first edge from the start point to the first node. Okay, now we're using our turtle now, so we do mturtle dot move to, and we're going to move to the starting position, m start x, m start y. Okay, we're then going to use the lookat method that we defined in the last episode to look at m end x, m end y, so that will point the turtle in the direction of the end point, and we set our length, which is equal to the edge length that we've just computed, like so. And we then make our turtle step. We call mturtle.step, and that will make our turtle move. We're not bothering to draw anything. That's really important. We're only using the turtle here to calculate our coordinates. So now we can store those. mx2 dot pushback m turtle dot get x. Okay, and my2 dot pushback m turtle dot get y. So you see what we've done. We've stored right up here at the beginning. We stored mx1 and my1. We put the first values in as being the start points. The second points then are calculated by positioning our turtle at the start point, pointing it towards the end point, setting the length to the edge length that we've calculated here, and then calling the step method to make it move, and then retrieving the x and y coordinates of where the turtle has ended up. Now we need to loop through each node and define the appropriate edges. Okay, so again we're going to do that using the modern C++ syntax for auto reference current angle. in M node angle. Okay, so current angle will be set to equal each angle in the M node angle array in turn. And we set the start point for this edge. Okay, mx1 dot push back. Okay, m turtle dot get x. Okay, and my1 dot push back m turtle dot get y. Just like that. Okay, notice that the start point of this edge is equal to the end point of the previous edge. Okay, right, and then we're going to rotate the turtle. Rotate the turtle according to the node. Okay, so m turtle dot rotate left. Note that we use rotate left and current angle, like so. And then we call step the turtle. Step the turtle according, step the turtle to the new position. Okay, m turtle dot step. Now notice that, of course, we've already defined the length. We've already set the length to edge length here, and we never change that. Okay, so all of the edges are necessarily the same length. And finally, we store the endpoint for, store the endpoint for this edge. mx2 dot push back m turtle dot get x, and then y2 push back m turtle dot get y. Okay, and then we end our loop. So that will loop through each node that has been defined by the user, and we'll use the turtle to calculate the new positions. So we set the start point for this edge as being the end point of the previous edge, and we'll then rotate the turtle according to the angle that's been specified, steps the turtle to move it to the new position, and then retrieves that position and stores that to store the end points for this edge, and then simply repeats that process for each node that the user has defined. And finally, handle the last edge. Okay, the last edge takes us from wherever we are now to the end point. Okay, so it is possible, if you're not careful with how you specify the angles, for the last edge to be longer or shorter, but we don't worry about that. Push back m turtle dot get x, so we set the start position as being the end position of the previous edge. Push back m turtle dot get y, and then the end point of this edge, push back, is simply m end x, and my2 push back is m end y, just like that. Okay, and then we close those. Okay, and then we close those. Apologies for my phone notification there. I don't know if you'll have heard that. And that is actually everything that we need for QB VK generator. So we've defined all of the methods. So we've gone over really how to compute the number of segments and hence the edge length. We've gone over that code there. I think if you pause the video there, and as I've said, if it's not clear, if you work through the geometry with a pen and paper, you should be able to see what we're doing, and it shouldn't be too difficult. Okay, so that's everything we need there. Now, if we go back to capp.h, so in capp.h we already added, yes, we've added an instance here of our new generator class. That's fine. So now in capp.cpp, we need to modify this to actually do something so that we can see the output. Okay, so we go to capp.cpp, and what we're going to do is simply, this is the code that we wrote before, and we don't need any of that. Okay, let's just clear all of that there. Yeah, so we'll just delete all of that. Okay, so starting from here, so just after SDL render clear, which clears the screen, we are in the onInit method, the onInit function in capp.cpp, and just after where we clear the window with SDL render clear, we're going to put in our new code. Okay, so the first thing that we're going to do is set the render draw color of p renderer, and we're going to set it to white. Like so, we've set the background to black, so it makes sense to make everything in white. Now, we're going to configure our instance of the QB VK generator class. So mvk generator. I'm going to set our start point. Now, just for this demonstration, we're going to set only really sort of very fixed. We're just going to do a simple demonstration. We're not going to create a Koch curve anyway. So let's set that to something like 245 by 240, like so. And then MVK, oh, come on, generator, set endpoint. Let's set our endpoint to say 395 by 340, like so. And then let's define some nodes. Okay, VK generator add node. So we're going to go with the classic layout, or the classic generator, as I showed in the diagrams we were looking at. So we had two nodes, one of 60 and one of minus 120F. So that matches the diagram that we had before. And then we call the compute method to actually compute everything. Now what we're going to do to actually display that, I'm just going to put some code in here to loop through everything and draw what we need to do. So we're just going to define float x1, y1, x2, y2, like so. And then we are going to do for int I equals 0, I less than m, vk generator dot num edges, okay, plus I, like so. And then we're going to call mvk generator dot get edge, and then we pass a reference to x1, reference to y1, reference to x2, and reference to y2, and our index, which is I. And then all we have to do is use SDL render draw line p renderer. Let's drop down to a new line, and then static cast these to integers. Static cast to int of round x1, comma, static cast to int round y1, okay, comma, static cast int round x2, static cast to int round y2, and 3 brackets. Okay, and that is everything. If we save that now that should be everything that we need. We've defined our QBVK generator class, which allows us to create instances of our generator, and we've set that up using the same node angle configuration that we talked about in our diagram. So that's this setup here, so we should get this shape. So whatever start point and end point we specify, we should get this shape in between those with a length everything scaled accordingly. And we set our first node to 60 and our second node to minus 120. Okay, so let's save that. Now if we go to our terminal window, let's open the terminal window. Okay, and there are, oops. Now terminal window, there we have our files. Now we need to compile that. So we do g++ -o main, that's the output we want, main.cpp, and then we want capp.cpp, and we need qb vk generator.cpp and qb turtle.cpp and -l sdl2 to tell the linker to link against the SDL library. And hopefully that should work. Okay. What have I missed? Does not name a type QBVK generator. In capp.h, of course, apologies, we also need, of course, to hash include, there we go, QBVK generator.h that we've just defined, of course. So in capp.h, we have to put this line in to include that, of course. Okay, so back to our terminal window. Now, hopefully, that should work. Nope. Now what are we missing? Okay, right. Now, yes. Okay, this is a really interesting point, and this actually demonstrates the importance of include guards. Okay, so we have this error, a redefinition of class QBTurtle. And the reason this happens, if we look in QBTurtle.h, when we wrote this before, when I wrote this before, I actually misspelled the include guard. Okay, so I missed out the _h there. So we check if ndef, if QBTurtle_h is not defined, then we hash define QBTurtle_h. Because I'd missed out that h, that test was obviously never succeeding, and so we were getting multiple definitions of the QBTurtle class, which leads to that error that we've just seen. A really interesting demo. Actually, I'm really glad that happened, because it's a good excuse to show why include guards are really important. Now, there are alternatives to include guards. There's the hash pragma once command, but personally I prefer to use include guards. Now, if we compile that now, that should work successfully. Yes, it does. So now let's run our code, /main, and there we go. There we are. So I should rename the window to something else, but there we see that is our shape, and we've defined it between a completely arbitrary start point and end point. So if we just close that, and let's go back to our code in capp.h, and we can show we can actually define this using any points that we like. So let's set the start point. Where have we got? So we are going to be in the middle 320, 240, 140.0f, and set our endpoint to be also 320 on, no, 320, 320 is the middle, 220, and then we want to go to 420 and 140f. Okay, and save that. So x goes from 220 to 420, y stays at 140. So let's have a look. Let's just run our compiler again and run our code. And yes, we now see we have a completely different shape. And in fact, you can experiment as much as you like with the start point and end points, and especially changing the length. If I make that shorter, so just 320, so it'll now be only 100 units long, we should see that everything scales accordingly. Run that. Okay, yes. And there we see, yes, so now it's much smaller, but not only is this shorter, but you see every line has got shorter, and that's really important. So there's a lot you can do, play around with that code, experiment with adding different nodes. In fact, I mean, let's just show an example of how that works. Let's make it longer again. Okay, and I just want to show why this is quite a powerful way of doing things. So that gives us a very simple shape, but let's add a couple more nodes and show how we can make something more complicated. Okay, so if we add another node now, if we set the angle to 0, then that simply won't change the angle. Okay, so that will mean carry on in the angle we're already going in, the direction we're already heading. And then we're going to add another node here, which is going to be, what are we going to need to go from minus 120, we need to go back, it's going to be plus 120f. Okay, so we've added 2 more nodes, and now let's have a look at that now. Let's compile that again. Okay, and if we run that now, yes. So now we see we can define a much more complicated shape, and everything still fits. So the number of segments has now clearly increased. So we have 1, 2, 3, 4 segments now, and we see that the number of edges is 1, 2, 3, 4, 5, 6. Okay, so like I say, play around with that. You can use it to create sort of any kind of complicated shape, except the first edge and the last edge are fixed. You can use it to create square edges, you can create these sawtooth type edges, all sorts of things. And that gives us a great deal of flexibility when it comes to actually creating the von Koch curves. We can play around and get all sorts of different results. So that's actually everything I really wanted to talk about today. I didn't want this to be a terribly long video. In the next episode, we're going to look at how we would actually create a class to handle the initiator, the shape as that we start with at the beginning, and how we'd actually then write the recursive algorithm to implement multiple copies of this generator to give the final result. As you can see, it maybe seems a little bit more complicated than it needs to be. To do a very basic von Koch curve does not need to be as complicated as this. The reason I chose to go down this road is because I wanted to create something that was more generic and that we could use to create a variety of different shapes. And as we've seen with these simple demonstrations here, the generator class that we've come up with is actually quite a powerful solution. And we can specify any number of nodes, and we can specify arbitrary angles at each node, and we can create some quite complex results. And when we come to actually look at generating the von Koch curves in the next episode, you'll see how that can really be used to create some really quite exciting, I think, quite interesting results. But that's everything for today. I hope you've liked this video. If you have, please do remember to hit that like button. And yeah, please remember to subscribe to my channel so you don't have to miss any future videos. Anyway, listen, it's really been a pleasure. I hope you've enjoyed it. and found it interesting. Let me know in the comments what you think, if you have any questions. The geometry might be a little bit confusing, but I'm quite confident if you work through it with a pen and paper yourself, particularly with reference to the code that we've written, I think you'll understand how it works. It's not too complicated, it's maybe a little bit confusing. I had quite an interesting time coming up with the algorithm for that. And yeah, like I say, let me know in the comments what you think. Anyway, thank you very much for watching, and I really look forward to seeing you in the next video. Bye!